Hi everybody, good morning. Ute, where are you? Thank you very much for the invitation and for organizing the event. No screen. Okay, I have quite a few slides and only 40 minutes, so I apologize in advance for not going into the depth I would like to go into on some of the issues. Good, so let us get started. Well, the outline of the talk will be quite simple, a short introduction, short discussion on criterions and definitions, some details on the examples of quantum mechanics and Einstein, the third quantum revolution, which I will define. It's a revolution that has not happened yet, and the hard road to the third quantum revolution, and some comments and conclusion. So to begin with, I'm not a historian of science, and I'm a quantum physicist, so I will say very little about the past and talk mainly about the future. And the future is the third quantum revolution, in my field at least, that has not happened yet. And it's interesting to analyze how it may happen. Will it come from as a revolution without revolutionaries, for example? Will it be an evolution rather than a revolution? Okay, so what is the third quantum revolution? Very briefly, later on I'll come back to it. The third quantum revolution is really a crack in quantum mechanics. We have quantum mechanics now for 100 years. It's a well-established theory, but we are all thinking that perhaps, maybe even hoping, it's not the end of the road. We're talking about an extension in the same way that relativity was an extension of Newtonian mechanics. So some of the things will not be broken, but we will be able to make better predictions. That's what a good theory or a better theory is all about. Okay, so we all, of course, know Kuhn, Thomas Kuhn. He was in Harvard, Berkeley, Princeton, MIT. He really went through some of the best places, and he talked about paradigm shifts. A very interesting idea, by the way. He was not the first. This was in 1962, his book, and of course, very quickly afterwards, the battle on his ideas ensued. There was a conference in London in 1965. Karl Popper was presiding, and the discussion has not stopped since then. So do we have revolutions, just evolutions in science? And if we have revolutions, are they made by revolutionaries? So these are all questions that are very interesting to debate. And why? Not just because of history, because it might help us educate the young generation in a better way. If we can educate more revolutionaries or scientists that bring revolutions, science will go forward faster. So these are very important questions in education, how to manage the money in science, and so on. Okay, so there are many, many papers, of course, and books on revolutionary science, and this is one I picked up because I like the abstract, but they claim, as you see in the underlined sentences, that having gone over all these revolutions in the table, it's hard to see, but you know most of them, they cannot find one specific reason. So they talk about puzzle solving, serendipity, inspiration, convergence of all kinds of observations, and they say that it's difficult to draw a clear distinction between normal and revolutionary science. So it's really at the end of the day, you have some evolution, but you have gradients, and the gradients of the pace of this evolution change. And these gradients, at some point, you have to call, or don't, revolutions. So it's about measuring these gradients of scientific pace, okay? And you can find very interesting quantification attempts. So this paper from 23, which has a lot of graphs, I bring here only two, shows something very interesting. So they take, for example, only up to, not current days, but you see here they look at individual scientists, yeah? And they look at their scientific production. And you can see that some scientists have much more scientific production than the average, yeah? And of course, they also analyze the connection between discoveries in different countries, and these are the different colors for the countries, and the economic situation of those countries. And of course, there's a very strong correlation there that works both ways. So there are many things you can do by analyzing revolutions in science. Very interesting topic. Okay, but I will not go into that. I hope that others that are philosophers of science, historians of science, will deal with all those interesting studies. And I've looked through the definitions. I found many. The definitions are very hard for what is a revolution and what is a revolutionary. So I'll use my own simple, very simple, simplified definitions. So for me, the criterion for a real revolution is that it's so outrageous. It goes against the paradigm we were educated on. Sometimes Einstein called it the nonsense of common sense, this paradigm that we were educated on. So it's so outrageous that everybody hates it, including the inventors themselves. Yeah? So that, for me, if even the inventors don't believe it, that constitutes a real revolution, or think that it's very strange. Darwin is one of my favorite examples, because he wrote to a friend that for him, admitting that his theory is right is as hard as admitting to committing a murder. For him, he was religious, by the way, and it also hurt his religious feelings. It was like committing a murder. So for me, that constitutes a revolution. And revolutionary, well, for me it means that he or she were very crucial at the time. And that means that one may believe that if they did not exist, the understanding they gave rise to would have come only after a very long time. So that is for me the criterion for a revolutionary person. And under those criterions and definitions, one can start analyzing different revolutions that happened. Okay, I'm going to only talk about quantum mechanics today and relativity. Those are things I deal with, but I won't go into technical details and talk very generally, because I know that many of you are not physicists. So later today we'll hear about Max Planck and Otto Stern, two giants of quantum mechanics. I will not say anything about them, but I do want to talk about three other giants of quantum mechanics. That's Schrödinger, de Broglie, and Einstein. Well, they meet my criterion of the inventor hating his invention. So Schrödinger hated quantum mechanics, wrote very interesting things to Bohr about how he wants to live it, and invented the famous Schrödinger cat, dead or alive, just to show his distaste for quantum mechanics. De Broglie really hated quantum mechanics, and he actually wouldn't teach it in university, and he fired anybody who wanted to teach quantum mechanics in France, and the French scientists still think that he delayed the development of quantum mechanics by 10 or 20 years in France. He later, together with David Bohm, developed Bohmian mechanics, which is sort of an alternative language. I will mention that. And Einstein, of course, hated quantum mechanics, said that God does not play with dice, although he was one of the initiators of quantum mechanics. He wrote the famous 1935 EPR paper saying quantum mechanics is incomplete, and until his dying day, tried to disprove the theory. So 3 giants of quantum mechanics who hated it, and therefore, for me, this is really a revolution. Of course, you can go into more scientific details and say that it was a paradigm shift because there was loss of determinism for the first time, loss of locality for the first time, loss of reality independent of observation for the first time. So when you go down to the details, you also find a paradigm shift. Okay, so now the question of revolutionaries. Were there revolutionaries for quantum mechanics? Well, you see here, this is from the Solvay conference in 1927. Many fathers and mothers for quantum mechanics. And so when there's so many people involved, it's hard to pinpoint if any one of them is absolutely crucial. And if someone is not crucial, then according to the definition I just gave you, they are not real revolutionaries. All right. So let's look at the example of Einstein. Nearly 2,000 books about Albert Einstein and his theories, thousands of more scientific papers and articles. Einstein himself wrote quite a bit, as you see here, and quite a bit of children's books that I could find. This is one I like. You can't see the writing, but according to the 3 red lines that you see there, it says that Einstein's thought was the first to think of some problems, he was the first to think of some answers, and he was the first to dream some dreams. So according to this book, at least, he was definitely a revolutionary. But people can claim that even he grew up in some relevant context and predetermined knowledge. So that means it was part of some evolution. For example, there was the Michelson-Morley experiment that said that there's no ether, something very basic for Einstein. There were the Maxwell equations that inspired Einstein. There was, of course, Galileo Galilei that inspired Einstein with his notions of relativity, and many other things like Lorentz transformations, and even the mathematics was not developed by Einstein. You can look up the history of his mathematics, for example, in a museum in Prague. So it's a very hard question. And of course, even concepts that you all learn in relativity, like proper time, time dilation, contraction, all of those could be found, and I will not go through all of the examples, could be found before Einstein. Okay, so even with Einstein, one might argue against him being a revolutionary, as I said. However, for me, following my personal criterion, that one may believe that if they did not exist, the understanding they gave rise to would have come only after a very long time. Namely, they had a unique combination of courage and skill to integrate all the pieces of the puzzle. Einstein was indeed a revolutionary in my mind. And I want to add to courage and skill also one more criterion, and that is intuition. The abstract that I showed you before also talked about inspiration, that's close to intuition. And the reason why I talk about intuition is that, especially with people who are taught very strongly to think logically or rationally or analytically, sometimes that actually suppresses their intuition or large-scale intuition, so maybe it becomes more rare. And so I wanted to add that as an additional criterion. And Einstein himself, actually, you can think of asking him yourself as a Gedanken experiment, dear Einstein, were you a revolutionary? So I did, I asked him, were you a revolutionary? And he said, of course, that you need some skill, you need context, and so on. But I think he would also talk about inspiration and intuition, and the reason why I say that is because he said all kinds of strange sentences. He gave clues. For example, he said imagination is more important than knowledge. But more than that, he said he was religious. Einstein claimed continuously that he was a religious man. So he felt that within him there was something driving him that is more than just rational and logical thought. and you can read a lot about his religion. He wanted actually to start a new religion, and he called himself a religious non-believer, something like Spinoza's God. So not a God like most religious people these days think about, that interferes in the life or follows every individual. He was thinking about nature and about harmony with the universe. And he said very strong sentences like, science without religion is lame, but religion without science is blind. And another quote I like is that the human being is part of the universe. And when people think that they're separate from the universe, it's a kind of optical delusion of our consciousness. And the striving to free oneself from this delusion is the one true religion. That's what he talked about. And of course, many scientists repeated very similar things, like Carl Sagan, and so on. Okay, so let us go back to the third quantum revolution after this introduction, rather long introduction. So the first quantum revolution happened 100 years ago, plus minus. I already showed you this picture of the famous Solvay conference of 1927. Second quantum revolution that people talk about is quantum technology, the quantum computer, and so on. It actually started already in the middle of the 20th century with the laser, the transistor, the atomic clock. All of those came in the middle of the 20th century. And here you see a picture from a few years ago where we inaugurated the BGU Quantum Technology Lab. And you see there Serge Roche, who won the Nobel Prize, of course our former president, and Rainer Blatt, one of the pioneers of quantum computing. So that was the second quantum revolution that is now ongoing. And the third revolution, as I already mentioned, is to find a crack in quantum mechanics. And if one, on philosophical grounds, believes that reality is infinitely complex, and we're just studying nature for a few hundred years, so I think that on philosophical grounds, one must assume that there is something also beyond quantum mechanics, and that one day it will be found. And there are also people, quite a few people, that are giving us hints. For example, Nobel laureate Roger Penrose loves to say that the lack of unification between general relativity, Einstein's relativity, and quantum mechanics is so bad, the fact that we cannot unite them under one theoretical framework called quantum gravity, it's so bad that he thinks this is a proof, actually, that at least one of them, if not both, are fundamentally wrong. And other Nobel laureates like Hooft continuously criticize quantum mechanics. Of course, the famous John Bell, who said, quantum mechanics carries within itself the seeds of its own destruction. Okay, so will such a revolution require revolutionaries? Let's agree that this is a revolution. If quantum mechanics falls, or is extended, or we find a crack in it, it's a real revolution. Because it's such a successful theory for the last 100 years. Thousands of experiments have confirmed it, and all of our technology is working on it. So this will definitely be a revolution. Will it require revolutionaries? So, what kind of conceptual leap will be required? I just want to give you a taste of how hard it's going to be. So a lot of landmines, and these landmines are called in quantum mechanics no-go theories, where you cannot go. Proofs, mathematical proofs typically, that in many books and articles written on it, that you cannot go there in any future theory that you invent, or you cannot go there, you cannot go there. I call this the landmine field. And just to give you a few examples, Bell already in the 60s had a non-local hidden variable. What are hidden variables? If you have a deeper theory, if quantum mechanics is some average of a deeper theory, then we call that theory hidden variable theory. So there are some parameters we don't know about. So this has, people call it hidden variable theories, and John Bell already gave a mathematical proof in the 60s that we cannot have local means that it obeys the causality of Einstein. And no information can move faster than the speed of light. So this is called local in physics. And after that, many other people developed further these kinds of theorems, no-go theorems, like Ocean-Specker. And but the landmine I like the most is called GHZ. You see here the GHZ team. In the center is Daniel Greenberger, Here he's celebrating his 90th birthday, and on the right it's Anton Zeilinger, who was my postdoc advisor, and they really proved, he also won the Nobel, of course, a few years ago, they really proved with this GHZ state that any thought of hidden variables, or local hidden variables, or Einstein called it elements of reality, independent of the measurement. Before the measurement, if you assume that there is independent reality, you run into paradoxes. It's beautiful. So even if you're not a physicist, I really advise you to read about it in some popular article or in Wikipedia. All right, so John Bell said about all these landmines, all these no-go theorems, he said what is proven by impossibility proofs, no-go theorem, is the lack of imagination. So that's very funny. There's almost a century of proofs, no-go theorems, of where we cannot go, but there are very important scientists who say that they don't believe these no-go theorems, although I don't know of a proof, an actual mathematical proof against any of these no-go theories. But it's something to keep in mind. Okay, so let's try and make a preliminary analysis. How much time do I have?
15 minutes.
15 minutes. Let's try and make a preliminary analysis of this revolution and this minefield, and the revolutionaries that might be able to cross this minefield. So, will it come from a theoretician? I recognize here several theoreticians, and I'm going to say that it will probably not come from theoreticians, not because theoreticians are not very smart people, but because these days most theoreticians are in different fields. So the foundation of quantum mechanics actually gets very little attention from theoreticians, unfortunately. And this is part of the problem of unification of quantum mechanics and general relativity, the lack of more effort. Will it come from an experimentalist? I think it will, and I want to explain to you the reason. So although there is very strong confirmation bias in experiments that we do, experiments have several ways to teach us completely new things. First of all, precision experiments. Just this year we had an experiment about the G-2 of muons that went to 100 parts in a billion accuracy. So these are called precision experiments. Experiments in physics are becoming so accurate that it might be that at some decimal point, at some place after the point, some decimal place, we will find a deviation. And we need several sigma deviation, but the experiments are becoming so accurate that even if you are designing an experiment to confirm the standard model or quantum mechanics, you might find something else. But I think it will actually come from searches, and there are different kinds of searches. There are searches inside the standard model, but highly motivated, like searches for dark matter, which is highly motivated. Dark energy, the expansion, accelerating expansion of the universe, this is highly motivated because we have some initial data. There's searches outside the standard model, weakly motivated. For example, somebody decides to measure the correlation between the electron mass, which we think is constant, and the season of the year. If somebody goes to do such a crazy experiment, there's no motivation for that in any paradigm that we know of. And there are searches in between. For example, quantum gravity, people are still arguing whether there is a necessity for that. So if we find something in the lab, but it's a surprise, I will not say that a revolutionary mind gave us this surprise. It was some surprise that came maybe from an error in the lab. We didn't expect it. But if it comes from a completely unmotivated experiment, because of some inspiration, some scientist came up in the morning, woke up and said, today I checked the correlation between the electron mass and the sun flares. That's completely unmotivated. It came from his inspiration, intuition, and if he was correct or she was correct, then I would call this mind a revolutionary mind. Okay, so many people have been working hard to achieve the third quantum revolution. For 100 years now, people have tried to attack this theory. It's a really amazing effort. And as a humble example, I'm going to describe to you my own personal experience. Okay, so in the few minutes I have left, you're going to see now a description of my failed attempts to become a revolutionary. Okay, it was a long journey, but so far with no results. So, this is quite a sad story. So I will start with a little bit of humor. And so I looked back in my photos from the time when I was young, and I found the beginning of an aspiring revolutionary. Not very meaningful, but still fun. This is at the age of 15 or 16. And so, yeah. So doing crazy things, I think, is an important part of it. But then I started later on to get interested in the foundations of quantum mechanics, or the two pillars of modern physics, quantum mechanics and special relativity and general relativity, and the connection between them. And now I'll take you through it very quickly in very general language. So first of all, I looked up my first papers about it, and these hidden variables that I mentioned before. So my first paper on hidden variables was actually when I was a PhD student. And it's fun for me now to look back and see these papers. So I was looking for tests. In my soul, I was an experimentalist from day one, and I was always looking for a test, how we can test these hidden variables or deviations from the standard model. So this is an example for quantum, an example for relativity is this paper, also from when I was a PhD student, on something called tachyons. Tachyons are supposed to be particles moving faster than the speed of light. Yeah, so they're breaking Einstein's relativity in a sense. And so I was looking at how to do experiments to detect these tachyons. By the way, in the 70s, some people said that they detected tachyons, but those experiments later were proven to be faulty. Okay, I was lucky, but this paper on hidden variables was actually picked up by a philosopher in Maryland. He is now in Maryland, and he wrote here in this, in his book, Interpretations of the Quantum World, about my search for deviations. And I was very lucky that CERN actually picked it up and decided to do the experiment. So that was the first time I really managed to convince somebody to do an experiment to go outside the standard model. Okay, so do we really understand relativity? Some people claim we don't. And going back to John Bell, you can find it on Wikipedia. He used to say that he's going around between physicists just to prove to them that they don't understand relativity. He had a question, and that question was about two spaceships that take off from Earth, and they accelerate with the same engines, exactly identically, and there's a rod between them, a stiff rod between them. Now the question was very simple: will the rod break or not? This became known as the Bell's spaceship paradox, and he claimed that most physicists get the answer wrong. Okay, that was just his way of saying that most physicists don't understand Lorentz contraction, which is a part of relativity. It means that objects seem to be shorter when they move at high velocity. So one of my early interests, was to try and find experiments that would teach us more about this Lorentz contraction, and this is an example. Perhaps the most impressive example of the foundation of quantum mechanics is the border between the classical world. We now see only classical things. We see one chair, we don't see a chair in a superposition. We see one person, we don't see him in a superposition. So the border between the classical world and the quantum world has really become one of the big questions of quantum mechanics. And many people claim that it's not understood. This is from a paper in Physics Today by Zurich. So on the left is the quantum world. On the right is the classical world. This is the border. Bohr is guiding the border here. Here's Schrödinger's dead and alive cat. And I like this quantum wheel of rights. Interfere if you can. This is the quantum wheel of rights. And this became a very hard problem. By the way, this problem even exists today in quantum computers. So most physicists believe that the transition is due to the environment. The environment, so from the classical world here, they send spies to the quantum world, and they bring them to the classical world, okay? like East Germany, West Germany style. And so the environment it's called environmental decoherence. But, for example, in this paper, we suggested that there's a completely different paradigm and that you don't need the environment for this move through the border between quantum and classical. So in this case, it's a completely different language than what is currently the consensus. Again, language, speaking of language, these two gentlemen, Bohm and De Broglie, developed a completely different language of quantum mechanics. The language we typically use is Bohrian language, but the language that they developed is called the De Broglie-Bohmian mechanics. It's a different language of quantum mechanics, and it's not taught in most universities, which is very unfortunate because I think language affects the mind, or the way the mind thinks. It localizes the mind in many ways, and these two gentlemen suggested a new language. It's not taught. So here's a paper that we wrote about why we think this language may be advantageous to try and get universities actually to teach it. Okay, and then I became experimentalist. So all this was theory. Then I became an experimentalist, and I came to Ben-Gurion University, and I had to also measure gravity, because that's part of general relativity, it's gravity. But when I came to Ben-Gurion, I felt that in this university things are a little bit upside down. Don't be angry at me. So the first thing I had to check is if in the Negev gravity behaves as usual. So I made this very primitive test, just jumping on sand dunes. But then I built the lab, and experiments became more refined. So here you see taking a clock. So what are these experiments about quantum gravity? You have to, if you want to test quantum gravity, you have to have an experiment that uses both theories in the same experiment. Without both theories, you cannot understand the experiment. So for example, as you see in the picture, if you take a clock and put it in two places at the same time, single clock, two places at the same time, that is quantum mechanics. Because only quantum mechanics allows you to put a single object in two places at the same time. But where is general relativity here? Well, general relativity, contrary to quantum mechanics, that says time is a constant parameter throughout the universe. General relativity says no, time changes throughout the universe depending how close you are to a massive object. So these two clocks, vertically above Earth, will feel a different time, but it's not two clocks, it's one clock measuring together at the same time, simultaneously, measure two different tick rates, two different times. So what will the clock see or measure in terms of time? So I won't go into the details, just to tell you these are the kind of experiments at the interface of general relativity and quantum mechanics that are trying to maybe find, as Roger Penrose puts it, what is wrong with one or both theories that they cannot be united. Also, it's good to try and use a different technique, very different than what other people are using. And here I went back 100 years to the Stern-Gerlach effect. I won't have time to go into it, and I don't need to, because my good friend Bretislav, sitting right in front of me, is going to give a talk about Otto Stern. Very interesting character, one of the first beautiful experiments of quantum mechanics. So I went back to this technique that was actually almost forgotten, and it's thought that I should start using it. By the way, he had to flee from Germany, died in Berkeley. Here you see actually Stern and Gerlach between them. Lisa Meitner, another very interesting figure, also had to escape Germany. She worked with Otto Hahn, and she was nominated something like 48 times to the Nobel Prize, never got it, for different reasons that people are researching. Okay, so with this Stern-Gerlach, we are trying to really test quantum gravity, as you see here, and one of the ways is to put a massive object. These are experiments we're doing now, a massive object, much heavier than atom, 10 orders of magnitude heavier than atom, in two places at the same time. And according to people like Roger Penrose, this actually, Einstein taught us that a massive object creates a curvature of space-time. You see it in all these beautiful pictures of Einstein's theory. But if you create a superposition of one mass, a superposition, then there's a superposition of space-time. There are two space-times that are living together simultaneously. And so many ideas are coming out of that it's highly unstable, crazy things are going to happen, and so on. And so this is really an attempt that we're now making for the first time to create a superposition of curved space-time. And the last example I will give you is this, again, general relativity, connecting between general relativity and quantum mechanics, testing if on a superposition, quantum superposition, the equivalence principle that comes from Einstein relativity, if it works. And so this is a paper that was put in the archive this year, and a good sign. It's the first time one of my papers has attracted enormous opposition in the community, so I'm very happy. It's very hard to publish this paper, so that's a good sign. But anyway, so much so that you could find on the internet this 1 hour long online podcast where Roger Penrose, Nobel laureate Roger Penrose, and his colleague Yvette Fuentes are trying to explain why our experiment is actually correct and why it's important. So that's it for examples. So my conclusion so far is that I failed, one of many who tried to become a revolutionary on the topic of quantum mechanics, the third quantum revolution, still trying. The good news is that quite a few funding agencies are still interested in it, and they have calls like this, tabletop physics that will transform our understanding of the universe. And I give some names here in case you want to submit some crazy ideas. So I have full respect for these funding agencies, and it's very lucky for me that these funding agencies are still have quantum mechanics high on their agenda, the foundations of quantum mechanics high on the agenda. Okay, I need to finish, and speaking of revolutions, my family comes from Rehovot, which is an hour from here, and I would like to congratulate the 2025 Nobel laureate in chemistry, whose family also comes from the area of Rehovot. Maybe you've not heard of him. Omar Gagi. He's Palestinian. His family comes from Asmia. And so this is nice to acknowledge. And here you see our former president giving him the Wolf Prize several years ago. And now he got the Nobel. And one last comment I have to tell you about is this. So last and definitely least, it's an advertisement. So if you don't like advertisement, close your ears and eyes. Well, the quantum and AI revolutions are also connected to the fundamental question of free will, which you have not mentioned so far, but free will is connected to creativity. And creativity is a word very much connected to the question of revolutionaries. I didn't mention creativity so far because it's so hard to define, although people are trying to quantify it. And so the question is, in the world population, are there really rare and enormous peaks of personal creativity? I showed you a graph in the start of the talk where people are trying to quantify productivity, scientific productivity, and you see these tiny, all of the scientists are down there, and you see these very individual peaks, dots, that maybe are telling us that yes, there's evolution, scientific evolution, but there are peaks of scientific productivity in some individuals. So that may be connected to the question of free will and creativity, which is sort of maybe different in different people. And so if you're interested in all that, you can look up my book. That's why it's an advertisement that came out this year and talks about the quantum mind, free will, creativity, and all that. And I hope you enjoy it. So let me conclude. So the definitions of what qualifies as a revolution and what as a revolutionary mind are complex and very hard. I actually think that Kuhn was somewhat right, at least. But it's really a delicate matter of definitions. And the hard measurement, it's really about the hard measurement of the gradients of accumulation of knowledge. So if you follow the accumulation of knowledge, and the gradients all the time change, and we saw some graphs in the beginning, and if you have a threshold gradient, and you say, okay, above this gradient, this is for me a revolution in some field, then you might agree that there are revolutions. But it's all about these gradients of accumulation. Regarding the revolutionaries, it's even a harder question. The answer is somewhere in the middle. Revolutionaries exist, but they're born in pre-existing contexts. I showed you even for Einstein, a lot of pre-existing context and knowledge, which allowed their brain to make the leap. So revolutionaries are still part of an evolution, and as such could have been replaced by someone else at some later date. We can only hypothesize about Einstein, of course. And still, revolutionaries are probably unique and rare in that they have both the courage and the skill. And then I added also intuition, inspiration, to combine and integrate the different pieces of the puzzle to one fundamental picture. So, again, ending with humor, a little bit of humor, I show you this picture, which I found in my archives. So, to end with a little bit of personal humor, my friends always knew I wanted to be a revolutionary. So in one of my birthday parties, they built a brick wall. Then there was this song, We Don't Need No Education, by Pink Floyd, and The Wall, it was called The Wall. So in one of my birthday parties, they built a brick wall and asked me to jump through it and break it, the dream of every revolutionary. So here you see my failed attempt that nearly got me killed. You see my leg there. I crashed. This was maybe a sign of what was to become my career. But perhaps it was that early wall breaking many, many years ago that led me to the 21 Falling Walls Award in Berlin, which was very moving for me personally. So let me end by thanking all my students and collaborators over the years. It was really a fascinating journey, very, very rewarding journey. And of course, thank you for listening.
We have time for one or two quick questions, and then we need to continue. Okay?
Many questions.
We can't hear you, I think, but...
Okay, I speak like that. First of all, what you said about the surprise that comes from unmotivated experiments that makes somebody revolutionary, it reminds me of the Copenhagen interpretation of Niels Bohr that makes Max Delbrück, another Nobel laureate, look for other laws of life. And then his student, Jim Watson, found the double helix structure of DNA. And Delbrück understood that he was on the wrong track, and he admitted that the solution had come from chemistry. And so maybe there is something similar over there, that you can overcome this romantic idea of revolutionary breaking this wall or something like that. And another comment, Darwin was not a revolutionary. Simply not. The revolution was already there, and he was a materialist person, and that's why he had enemies, but not because of the idea of evolution.
Well, first of all, Darwin hated his invention, and that's what I emphasize.
What was his invention?
No, his book, whatever you want to call it, that had many editions, and by the way, it was not fully formulated. Even between his editions, he changed a lot. The book changed a lot between his different editions. So we can argue about it later, but I still claim that he contributed a very strong gradient to the idea of evolution.
Another question, we have time because it takes time to arrange the computer. Yes, Sebastian.
I don't think there's too much difficulty in identifying scientific revolutions, right? So why is it so difficult in identifying the people behind those revolutions?
Well, as I said, even if you take Einstein, which is really the example for a revolutionary mind, you find that there's so much pre-existing knowledge, that that you can debate it. For me, he was a revolutionary mind, but you can definitely debate it if you look. And so each person you take and you ask, was he a revolutionary mind? It's all about, at the end, the definitions. How much pre-existing knowledge are you willing to accept before he loses the title? So, he or she. So it's really a question of definitions, and quantification is very, very hard in these questions.
Yes, please.
I want to suggest that looking for cracks is not the fact that is typical for the revolution or revolutionary, and Einstein is a great example. He wasn't looking for cracks. The revolution comes from people who noticed the cracks and created a new frame using new language, new concepts, and this became the revolution, not the cracks themselves.
Thank you for that comment. I think with quantum mechanics it's different than many of the other examples. And by the way, in the abstract that I showed in the beginning, they claim that really each revolution has its own path and own background. But quantum mechanics, now after 100 years of high precision experiments, yeah. So my intuition is that you will not be, there are no cracks, okay, no cracks, let's start with that. And so the big challenge now is the crack. After that, there will be a huge wave of ideas why this crack happened. But now the big, after 100 years of experiments, at 100 parts per billion precision, now we're looking for a crack. That will be the big change in the story case of quantum mechanics. Before we talk about anything else.
I completely agree, but what I say is that looking for the cracks is what everybody does. The revolution is doing something completely different.
In quantum mechanics, at least, I can tell you as an experimentalist, most experimentalists in quantum mechanics are not looking for cracks. That I can tell you for sure.
So, thank you, Juan. Thank you very much.
Sure.
So,